Hello again, this is Galen Pickett, Cal State Long Beach, Department of Physics. This is Physics 151, and now I want to talk about rotational angular momentum. This is the internal angular momentum in the system, Chapter 11, Section 2. So here's a situation that I want you to think about. I've got an object of mass m, and it's got a velocity that I know. It's got v in the x direction and nothing in the y or the z. And it is coming in, it is going to hit this stick, and this stick has a moment of inertia of 0. Here is a frictionless bearing, so the stick can rotate freely once the object is hit. But it's going to hit at a distance off axis of y0. So here's the final state. y0 is the radius at which this object is spinning around. So what we know in the initial state is the angular momentum. We can calculate what the orbital angular momentum of this object is, and it's equal to r cross the momentum, and that's I, j, k. So the initial position, I've got x, which is changing with time, but the y0 does not change. The y0 is the same. It's coming straight into the stick. And then 0 in z. The momentum has got mv in the x direction, 0 in y, and 0 in z. As usual, I'm going to get 0 for the x direction and 0 for the y direction. It is the z direction that I've got to, that's interesting. So I've got k hat times x times 0, which is 0, minus mv times y0. And that is what the initial angular momentum is. It is negative k hat mv y0. So that is the initial orbital angular momentum of the system. Now after the collision, this moment of inertia is 0. There's no there's certainly forces from the surroundings. There's a force continually changing the momentum of this object. It's going to go around in a circle forever, so there is a inward force. That inward force, however, is acting right here at the axle, and it's perpendicular to this velocity, so it doesn't do any work, but it does change the momentum. What it will not change is the angular momentum, because this force points perpendicular to the direction of motion. This force can't make it spin faster or slower. So somehow, even though this object is now no longer going on in a straight line, the L in the final state has got to be the same thing, this minus k hat m v y0. Well, because the stick has a moment of inertia of 0, I know that the speed of the ball, the only thing that the stick does is it changes the direction that the ball is going. So the speed, the magnitude of the velocity vector of the ball is going to be the same as it was in the initial state. So that I'm going to be able to calculate what the angular velocity is. It's just going to be v divided by y0. So that's what the angular velocity in the final state is. So I could write this as the v, the speed with which the ball goes around this circle, is equal to omega final times y0. And then I could take this v and substitute it in there to find something about what the final angular momentum is. So that's minus k hat times m times omega final times y0. That's the v times a y0. Now the reason I want to do that, I've got a direction for this. So it's the final angular momentum spin points into the screen, just the same way the initial angular momentum pointed into the screen, so that didn't change. I'll then combine all the factors in this expression that depend on the ball and the stick. That's the m, the y0, and the y0, into one thing, m y0 squared. And you might recognize that as the moment of inertia of this ball plus stick system. I then multiply it by omega final. And here I'm using omega final as a positive number. So the final angular momentum is minus k hat, the rotational mass, times the rotational velocity, and I could just write this as I times omega final as a vector. And you can compare this to the linear momentum. P is equal to the linear mass times the linear velocity. It's exactly the same expression. The spin angular velocity depends on how fast you're spinning and what is your reaction to spinning. What is the inertia to make you spin faster or slower?